In this video, I'm going to give a brief overview of the questions in midterm 1 review. So I'll talk about the solutions so you can check and get ideas about what it will be covered in the midterm 1. Okay, so let's get started. So first set of questions about eigenvalue and eigenvectors. So those will be mainly based on the homework 1 that was assigned at the very beginning of the course. So basically, if I give you a matrix A, so it's a square matrix A, and if lambda is eigenvalue of A, so what can we say about the eigenvalue of A minus A inverse plus A squared? Okay, so here we actually use the property for the eigenvalue matrix A. If lambda is a eigenvalue matrix A, so as shown in homework 1, so the A inverse will have the eigenvalue of lambda minus lambda inverse as well. So assuming here lambda is not equal to 0, and A squared will have the eigenvalue of lambda squared. And so we can, if we put them together, we have A inverse plus A squared will have eigenvalue of lambda inverse plus lambda squared. The reason we can say here is, so lambda is eigenvalue of A, assuming the eigenvector is alpha, for example. So I have A times alpha is equal to lambda alpha. So we can multiply both sides by A. Let's say do A and A. So this will be A squared times alpha. And this will be, you can swap the alpha to lambda, because lambda is scalar. So lambda A alpha. So A alpha again, so according to the eigenvalue, eigenvector, so this is lambda. So this is equal to lambda times alpha. So it's a lambda squared times alpha, which means it doesn't change the eigenvector actually. It's only the eigenvalue will change, but eigenvector won't change. You can also add on, so you can say A inverse. So if I have A alpha equal to lambda alpha, so you can also multiply both sides by A inverse. A inverse. So that give you the property is this is alpha equal to lambda A inverse alpha. Of course, I can do this, put lambda to the left hand side, so 1 over lambda alpha equal to A inverse alpha. So that actually shows the A inverse have eigenvalue 1 over lambda and eigenvector is alpha. That's it. Okay. So actually, if you put them together, if you put them this two together, you get A squared plus 1 minus lambda times alpha is equal to, oh no, sorry, let's be A inverse alpha. So this side plus this side, and this side plus this side, you have equal to lambda squared plus 1 over lambda alpha. Okay, so it means this is eigenvalue of the matrix A squared plus A inverse, and alpha is still its eigenvector, which actually solves the second problem. If alpha is eigenvector of A minus A inverse plus A squared associated with eigenvalue, now the same one, okay, sorry, it's opposite. If alpha is eigenvector of A associated with eigenvalue lambda, the same eigenvector is eigenvectors of A inverse plus A squared associated with this eigenvector, which we already showed right here. Okay. So which means if we do A squared, even A cubed, you can follow the same property. The second kind of question is about a matrix norm, okay, or vector norm matrix norm. So here's questions about how to compute the spectral norm of a matrix, a square matrix. Okay, so here give you a matrix A, okay, which is 4, 2, 2, 1, and here's pay attention to the question is compute the spectral norm of A squared. Okay, so this is different from the spectral norm of A. Okay, don't compute just spectral norm of A. Okay, to compute spectral norm of A squared, now we have to compute A squared. So we can do the calculation just the matrix product. Okay, this is compute A squared. Then the spectral norm is defined as the maximum of the eigenvalues of A, the matrix S itself transpose time itself. Okay, this was the definition of the spectral norm. Of course, you can also do opposite. You can also do A squared transpose. That's the same. Okay, it doesn't change the eigenvalue because the transpose and the self is the same, have the same eigenvalue. Okay, so pay attention to here because I'm talking about the spectral norm of a squared. You do a squared transpose times a squared. So don't use a transpose times a. Now then it's computing the spectral norm of a instead of a squared. Okay, so don't do that. Once you do that, we do make maximum eigenvalue of a squared because here a squared is symmetric. This is symmetric. So a square transpose is the same as a square. So this is a square, and a square times a square is a to the fourth. Okay, a to the fourth means okay, matrix to the fourth, right? I can do the absolute value, put it over here. So this is mean if you take a square root of that, is a maximum of lambda I of a squared. Okay, square of that, right? So here I just keep the number up here because that's the computer based on following. So don't do this number right now, but the number coming from the bottom computation. So in order to do that, we have to compute the eigenvalues of a. So the eigenvalue of a is computed by determinant of a minus lambda equal to 0, or you can do determinant of lambda minus a is the same, equal to 0. So if I compute a minus lambda I, it will be a minus lambda I. Lambda identity will be 1001 in this case. So when you do the calculation, that's a minus lambda I. So to compute determinant of that, so it's because it's 2 by 2 matrix, it's just product of the diagonal entries minus product of diagonal entries. Okay. So if we simplify a little bit, we have this is final equation we have. So it's lambda times lambda minus 5 equals 0. So actually we have two eigenvalues. One is 0, one is 5. So if you put them over here, so the maximum of lambda I squared. So if you do a lambda I squared, so lambda 1 squared, absolute value lambda 1 squared is just still 0. Lambda 2 absolute value squared is 25 because it's 5, absolute value is still 5, and you do a square 25. So the maximum value is 25. For this guy, it will be 25, right? So that's why it get 25. Okay. The next question is about a span and the basis. So okay, it's talking about give you a set of vectors. What is the space, the span space, and then what is the basis for the set of vectors? Okay, so the definition of span is pretty standard. It's pretty straightforward. It's just a linear combination, weighted linear combination of all these vectors we have. So you can do f1 x1 plus f2 x2 plus f3 x3, so on and so forth. So this alpha 1 until alpha 5, they're actually real numbers. Okay, that's it. So you just can reach whatever space can reach. So you got a span. So dimension of this guy is 3. The reason this is 3 that you can sort of this thinking in this way. First of all, x1, x2 they're independent. So dimension talking about the max number of independent vector in the set of vectors in this 5. How many of those are linearly independent? Okay, so first of all, we saw x1, x2 they're independent because this is first entry of this non-zero, but the other entry is all 0. And this guy, the second entry is non-zero, but the first entry, the other entry is 0. So you cannot do any linear combination. First one, get a weight to get a second one, right? Similarly for the third one, you can see right now over here, it's linearly independent of this first two because the third entry is 0. It doesn't matter what kind of linear combination you do, you never get a non-zero entry in the third entry because the third entry for x1 and x2 they're always 0. It doesn't matter what the linear combination is, still 0 for the third entry if you do the linear combination of a sum of x1 and x2. So this must be independent. So you know the first 3 they are linearly independent. And the matter of fact, x4 and x5 can be represented by a linear combination of the first 3 because you sort of can see x1, x2. If you do x4, right? So you can do x4 by some linear combination. The reason is this one, I can do 2. Okay, I can time 2. Okay, of this guy, I can form the first number right over here. Of course, I can use x1, cancel out x3. So if I do here, x4 is what? So the second entry is 0, right? And last entry is 1. So what I do, if I do, let's do over here. So I need to keep the last one to make sure they match because there's no other entries x1, x2 that can match it. So I have an x3, right? So I need to cancel out which term? The second one. Okay, so I have to -1/2 x2. That will cancel out this term, right? And also I want to get this one, another plus x1. that will give me x4, right? Because this x3, the last entry will match, okay? So this, but this has a 1. I want to cancel out because it has 0, right? So I do negative 1 half x2 will cancel out this term because this 0 doesn't do anything else. And x3, we have remaining one is 1, but I want 2 over here, right? So I just plus x1, this 1. So that will give, you can do the same thing, some linear combination to that, so which means x4 is not linear independent of x1, x2, x3. Okay, so that's dimension of this span is 3, okay? The basis is fairly easy to say. You can say x1, x2, x3. Okay, you can also say x1, 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 x2, x4 because x4 also have a non-zero entry in the third. You want to make sure that the third entry over here is non-zero to match, then to combine with x1, x2 will form the basis. Okay, you can also do x1, x2, x5, so it's okay. Yeah, but you need to just tell one of them. You don't have to tell as many as one. Just pick one. Okay. Okay, the next question is a little bit general question. It talks about linear independent rows and columns for a matrix, which may not be a square. It can be a square matrix. It can be have more columns than rows or more rows than columns. So that can be a little bit complicated. Okay, so to solve the problem, you basically can give an example. Let's say 2 by 3, 3 by 2 matrix. You can see what's happening. So let's see if A is m by n matrix, so m is number of rows and n is number of columns. Okay, for example, here is 2 by 3. So this example I give here is 2 by 3. Here is 2 by 3. So the m is 2, n is 3 in this case. Okay, so I'll draw it up here 2 and 3. So what is the maximum number of linear independent columns for this one? Okay, apparently here we have 3 columns. Okay, so but you only have 2, right? Because each column is two-dimensional vector, right? As I mentioned in the class, for n-dimensional vector, you have at most n column that are linearly independent. You cannot have more than that. So which means, hey, because I only have two it's two-dimensional vector. Even if I have 3 columns, but I have at least at most 2 linearly independent vectors. So which means here is m. Well, the number of linearly independent rows, of course, you take about rows, only have 2 rows. Of course, the maximum is 2. Yeah, this is mm. If m equal to n, yeah, you can have squared. Of course, you can still say m, or you can also say n because they're equivalent. Okay. If m is greater than n, it's like this case. You 3 by 2, for example, you have 3 columns, 2 columns, 3 rows. Even you have 3 rows, so number of linear columns, of course you only have 2 columns, right? So the smaller one determined, you can't have more than 3, right? You only have 2 columns, so the maximum is 2. Similarly, because of the maximum number of linear independent rows also 2. The reason is we only have 2-dimensional, right? We only have 2-dimensional. If you consider each one as a row, as a column, you can consider this as column if you do the transpose. So those one, because also two-dimensional one, so you can have at most 2 linear independent vectors. This is determined by the number of elements in each row. Only 2, so this is also n. So this is a general principle you can apply to find the maximum number of linear independent vectors, columns or rows for a matrix, a general matrix. Okay. The next question is about the positive definite and the negative definite matrices. So as I mentioned in class, to check if a matrix is positive definite or negative definite, or positive semi-definite, negative semi-definite, we need to check the symmetric portion of the Q, the matrix. Is positive definite or negative? You cannot check directly do not check the eigenvalues of the original matrix directly unless this Q is symmetric. Okay? So in other words, to check if the matrix is symmetric, first compute the symmetrical portion if it's not symmetric, and then check the symmetrical portion, eigenvalue symmetrical portion, to see if the eigenvalues are positive. If it's yes, positive definite. If the eigenvalues of the symmetrical portion of matrix Q is negative or negative, so we can see negative definite. If there's some positive, some negative, it's called indefinite, or it's not a positive definite, not a negative definite. Alright, let me give you an example. If I give matrix B, which is 1, 4, 0, 1, okay, apparently he's not symmetric. We have to verify it's symmetric or not. It's not symmetric. So you cannot use the eigenvalues of B directly to determine if it's a positive definite or not, even if the eigenvalues here are all positive. Okay? So we have to check the symmetrical portion of it. In order to pick the sigmoid approximation, we have to compute the B plus B transpose divided by 2. Okay, so as long as since we are given B, so we can compute the B transpose and divide by plus B transpose divided by 2. That's the symmetrical portion of it. So it's 1, 2, 2, 1. Okay, then we can compute eigenvalue of this matrix, the symmetrical portion of it. Okay, I want to go into detail about the computation, but it ends up having two eigenvalues which are 1 and -3. So they're not a positive definite, not negative definite. So this actually shows that it's not true. If you compute eigenvalues a bit directly, it's not correct because the symmetrical portion does show that the eigenvalues have both positive and negative values. Okay, so this is not a positive definite, not a negative definite. Okay, so the next question is about how to compute the linearizing of nonlinear system, which I already talked about in class. So basically, the idea is you write the system in this way because it's a nonlinear system. You don't have ABCD form. So typically we have x1 dot, x2 dot, x3 dot. You can have more if you have more state, right? So basically, you have x1 dot is a function. So this one we name it as f1 function. x2 dot is some function, f2 function. x3 dot is some function, f3 function. You can name it more functions if you have more variables. And alpha y state up, y is equal to x2, this function, and you name it as g function. Okay, this is first standard structure for the linear, how we do the linearization of nonlinear system. Okay, of course normally we'll have the nominal control input, nominal initial conditions, and nominal states, and even nominal outputs. Okay, that's what we have. So if you're not given, so you have to compute this nominal state and nominal output. You're given them. This will be given. So this should be given. So this may not be given. Okay, x tilde t and y tilde t, that's called nominal state, nominal output. If you're not given, compute it. So normally you should be able to compute it. It's typically in a special situations you can compute it. In general, you cannot compute the solution, but in some special cases, given the nominal control input and nominal state, you can compute the output. So in many cases, you are given this value to make your life easier. Okay, for example, this case, I give you a nominal state, which is t, 2t minus 3, t minus 2, which means the nominal state for the nominal of x1 is t, nominal x2 is 2t minus 3, nominal x3 is t minus 2. And my y output is just, nominal output is 1. Okay. So the goal is try to linearize the system around the nonlinear, the nominal state, nominal output, and nominal control input. Okay. So how do they do it? So as mentioned in class, if you're not given the nominal state, the nominal output, and nominal control input, you have the first step is to compute the ABCDs. Okay, that could be time invariant. So this is how we compute the AT, BT, CT, and DT. So AT actually is given by this form. Okay, it's partial f1 over partial x1, partial f2 over partial f1 over partial x2, partial f1. This is the first row. Okay, I don't want to repeat over here. So actually, these f functions are determined by those we already find out over here. So you just do a number of partial derivatives with respect to different variables. Okay, all right. So if you just give one, I probably do the second row because the first row is pretty straightforward. I do the second row, tell you how to do the partial derivatives. Okay, so f2 is u squared x1 plus x3. Okay. If you do this partial over partial x1, you consider all other variables, like u and x3, they are all constant. You just consider x1 as a variable. If you do a partial derivative, just push x1, so this is constant time x1. Your partial derivative, you just do the constant, okay? And minus x3, okay, because x3 is a constant, you take the derivative of x1, you get 0. That's why it's u2 squared, okay? Partial f2, partial x2, this is not a function x2, so it's 0. Partial f2 over partial x3, you consider u to be constant, x1 to be constant, and x3 is x3, okay? You partial f2, this first portion over partial x3, you get 0 because it's constant, take the derivative 0. And then minus x2, x3 over partial x3 is 1, because if I had added a minus sign, so it's a minus 1. So if you do other kind of calculations, of course, when you do that, you have to substitute every state, every variable, like u variable or x variable or whatever, by its tilde value, this nominal value. Okay, so we replace u tilde by u tilde, ut by u tilde t, so this will be u tilde t squared basically. Now u tilde t is 1, so u tilde t squared is also 1, so I replace by 1. Okay, because I replace this by tilde, you get 1. Okay, that's how I get a 80. So fortunately it's a constant. If I do the same thing for b sub t is partial f1 over partial u partial f2 over partial u partial f3 over partial u in this case. Okay, of course I have replaced everything I computed by x tilde value if it appears in the partial derivatives, in the computation of partial derivatives. Okay, so partial f1, if you do this one, partial u, you can see u as a variable, of course. The u squared with respect to u, you have 2u. Okay, and the second one, also you can see x3 as a variable, as constant, x1 as variable, constant. You only can see u squared, u as here as a variable. So u squared, x1 is constant. You can put a constant with a 2u squared. You take a derivative, you get 2ut times x1t. Okay. Now we have to replace u by u tilde and x by x tilde. So u tilde t is 1, okay? And so this is 2 times 1 is 2. 2 times u sub t is still 1 is 2. x1 by x tilde. So x tilde I like to do here. x1 tilde is t. So it's t over here. So it's 2 times t, okay? Simply do c and d. don't want to repeat over here. So this, you can compute the value over here, then replace every variable by its tilde value. So this is step 1. Step 2 is to define variable. Actually, the linearized system is not we cannot say is x dot t is y is right a t b t something like that. A t x t. We cannot. It's not like that. Actually written by x delta. X delta is defined x t minus x tilde t. Y delta y t minus y tilde t. U delta is u t minus u tilde t. If you do that, we have x tilde t is at plus approximately equal to atxt plus bt ut. Y delta is ctx delta plus dt u delta. Okay, so that's the delta change will satisfy the linear time invariant system. Okay, it's not an original system. Okay, the next question is about the computation of the transition matrix of linear time invariant system. So the transition matrix we're talking about typically is for a linear time invariant system transition matrix. Actually, because the linear time invariant system is a special case of linear time invariant system. Yes, of course, we can also compute a transition matrix for linear time invariant system. So if I give you a linear time invariant system over here and I give you initial condition x0, and I give some special value of a, for example, is a diagonal matrix, for example. Now you can compute the transition matrix of the linear time invariant, which is just given by e to the a sub t. Okay, that's this is transition matrix for linear time invariant system. Okay, that's this transition linear time invariant system. So the number of ways you can compute that. The first one, you can use the definition, because I know EAT has a definition of identity plus a sub t plus at squared divided by 2 factorial plus at to the cube divided by 3 factorial, so on and so forth. You can do that. It's a little bit complicated, okay? The second approach is you can use the inverse Laplace transform, which is e to the a sub t is L inverse of si minus a inverse. Okay? I don't want to compute the first one. Okay, it's a little bit complicated, but you can do it. Okay, we have to find the pattern. That's it. Okay, for the second one, you can do that. If I do that one, it's the si minus a inverse, then you take an inverse Laplace transform. Okay, once you do that, you can s times a. Identity here is just a 3 by 3 matrix. You put it over here. So identity here is 1 0 0 0 1 0 0 0 1. So it's 3-dimensional identity vector of the matrix is by this. The time s, okay, it's coming here. So this is then I put an a over here again. So I do the minus. Okay, I do the inverse. The inverse given by just this. Okay, you just do the inverse of each diagonal entry because it's diagonal matrix. And so the L inverse will be L inverse of each entry. Others are all zero, so we can ignore those. So L inverse of the diagonal entries. Okay, so this is just pretty straightforward. You take the table. Okay, use the table of the inverse Laplace transform. You can see this is e to the t and e to the 2t, e to 3t, and all other entries are 0. Okay, you only have a non-zero entry on diagonal entries. Okay, the other one, you can make your life much easier because this is diagonal matrix. You can also use the property for special cases. For the diagonal matrix, remember, for diagonal matrix. Of course, this is even more special because the diagonal are all constant, even not changing, not time dependent. So e to the at is phi t to 0, okay? So it's in integration of e to the integration of 0 to t1 d tau, okay? And the second one will be e to the 0 to t2 d tau. This is, if you check my video on the transition matrix, okay, I use transition matrix for linear time invariant system, and their special case is diagonal matrix, and you'll see that why I can compute the transition matrix in this way. So when you do the integration, you actually have the same form as the previous one, so that's the same result. Okay, so let's move to the next one, is computer transition matrix and the solution to linear time invariant system. This will be a little more complicated, but we can follow the steps I mentioned below to compute the transition matrix and the solution to linear time invariant systems. So what given the linear time invariant system is xt equal to 0, negative 1, 0, 0 t time xt, and 1, 0 ut, and yt is the 1, 0 time xt, okay? So first question, what is the transition matrix phi t and 0? Of course, when we talk about transition matrix, we're actually talking about this, okay? We're not talking about the original system, okay? Remember, you check my notes. Transition matrix talk about x dot t equal to at, okay? That's my transition matrix, okay? At, sorry, it's at xt, okay? The transition matrix is, because this is also again a special case, this a sub t is diagonal. So it follows the special case I mentioned in my video, so you can make your life easier. So the transition matrix is e to the integration of 0 to t, negative 1 d tau, and 0, 0, and e to the negative 0 to t tau. What I mentioned in my special case, you change everything, every variable in your diagonal entries from t to tau. Because this is only t, so I change it to tau, integrate from 0 to t, tau d tau. Okay, so replace every t by tau. Okay, so general case, if I have the diagonal matrix a sub t, which is a11t, a22t, ant, so its transition matrix is given by e to the integration of 0 to t, a11 tau d tau, and e to the integration of 0 to t, a22 tau d tau, and so on and so forth. That's how I can, so all the other entries are 0. Okay, over here. So if I do the calculation, so I can get a transition matrix phi t0, e negative t0, 0, e negative 1/2 t squared. If we do the integration, okay, don't do the computation. As a matter of fact, you also can have t and tau, which is equal to, so integration, when you have change this one to tau, okay, over here, so you actually change this one to tau, change this one to tau, change this one to tau. That's it. So when you do here, you actually have is integration 0 to, this is tau t, negative 1 d tau 0, and 0, this is e 0, and this is tau t tau d tau, somehow like that. So this will give us is this is e to that. So e is minus t minus tau. Okay, this is 0, 0. This is the e 1/2. 0 will be t squared minus tau squared. That's it. So that will be the if you have don't start at time 0. that's what happened. Okay. All right. So let's go. Now let's compute the solution to the linear time invariant system. Okay. So assume here is my initial condition that 1 is 0. My control input is 1, and make it a little bit simple for all the time beyond 0. And one computed y sub t. As I mentioned here, the y in class, so y sub t is equal to c sub t times phi t0 x0 plus integration from 0 to t c tau ct phi t tau b tau u tau. Okay, so of course here we already have we have c, already have c, right? Already have c already given. Okay, if c here is already given, so at, bt, ct they are given. So let's take a look. So ct is given, phi already calculated from the previous step, x0 already given, ct is given, phi tau already computed over here, and b tau and u to z are all given, so we can calculate that. Okay, if I do the calculation, so replace ct by 1, 0, that's a ct, and phi t0 is e minus t0, 0, e 1/2 t squared, and I guess 0 is already given, 1, 0, okay. The integration for the second one, integration of 0 to t, 1, 0, ct, phi is this, phi t is then replaced by here, okay. And I do ct, ut is 1, 0 d tau, okay. That's it, right? I don't have d. Actually, I don't have d over here because I don't have this dt ut. I don't have this term, so I can ignore the last one. Okay, if you do the calculation, okay, I should recalculate this again over here, so you can ignore because I already calculated over here. So the first time you can do the calculation pretty straightforward, e to the minus t if you do the matrix product. The second time you do the product again, you get this. Okay, the first product, this first two, you get this. And you do one more calculation, you get this, okay. So once you do the calculation, you actually get, what you get is this. You do the first one will keep the same. The last one is we do all this guy times this guy, which is e minus t minus tau. So we can separate them because I integrated with tau, so this is constant. I can move the outside. Now the inside, the integration with e tau over tau is still e tau, okay. Then this is still the same. I keep it over here. So e minus tau is I keep it over here. So e tau evaluated t and 0. So e to the t minus 1 because e to the 0 is 1. So it's equal to e minus t plus. So this product will be 1. This is minus e minus tau. So this then will cancel out. So actually we have the output is a constant. It's just equal to 1. Okay. So even if computation looks pretty complicated, but you can find a solution, and the y is equal to 1. So this is a general step that you can find a solution to the linear time invariant system. So the actual computation may be complex if you give, let's say if I change this to some other values, the computation may be complex. But you can find a solution to the linear time invariant system easily. First find the transition matrix, then try to use the transition matrix and the initial conditions, the control input, and the AT, BT, CT, DT value to compute the actual output. Okay, I hope this is sufficient for you to prepare for the midterm 1.